Faced with systemic teacher shortages, school administrations are increasingly forced to move secondary educators across both mathematics and science departments. This policy is driven by a simple administrative logic. Because both fields utilize quantitative data and linear procedures, their core teaching methods should be interchangeable. But pedagogical research suggests otherwise. These academic disciplines generate distinct subject cultures that resist this kind of generic integration. A subject culture is the underlying set of epistemological agreements within an academic tribe. It dictates how knowledge is organized, verified, and produced. These cultural boundaries structure a teacher's daily objectives. They dictate how an instructor perceives their students and how they define success in the classroom. By mapping these two distinct subject cultures, we can see why generic instructional principles often fail the specific demands of subject-specific teaching. The illusion of a generic STEM pedagogy sets up out-of-field teachers for failure because it ignores these underlying epistemological realities. To understand this friction, we have to analyze how raw academic disciplines translate into structured school curricula. In mathematics, structural organization is defined by a standardized, sequential progression. Content moves strictly from simple logic toward complex abstractions. This establishes a rigid system. Every concept acts as a prerequisite for the next, locking into place with no room for deviation. School science operates differently. It is not a single sequence, but a cluster of distinct disciplines, including physics, biology, and chemistry. Science is topic-based. It centers on the investigation of observable natural phenomena rather than the navigation of an isolated logical hierarchy. While mathematics textbooks are internationally standardized, the science curriculum is in constant flux, driven by the rapid pace of contemporary discovery. Math teachers navigate a predetermined sequence, whereas science teachers must constantly synthesize information from rapidly evolving and disparate fields of study. Treating these two fields as a monolith is structurally incoherent. A rigid ladder and a decentralized web cannot be navigated using the same pedagogical map. These divergent curriculum structures naturally select for different classroom behaviors and instructional priorities. In the math classroom, because the sequence is absolute, the objective is dictated by the need to overcome sequential hurdles. This results in a pedagogy of support. Here, the teacher's primary function is ensuring that no student breaks the sequential chain of logic. Instruction focuses on making isolated, abstract concepts temporarily concrete, providing just enough scaffolding to move the student to the next rung. In science, because the topics are disparate and phenomenon-driven, the objective shifts towards establishing relevance and curiosity. This creates a pedagogy of engagement. It prioritizes hands-on, experiential learning to anchor abstract theory to physical realities. Science teachers must actively translate science as facts into science as doing to maintain a cohesive narrative across disconnected topics. The math classroom focuses on moving students strictly upward. The science classroom focuses on reaching expansively outward. Possessing raw academic knowledge in a subject is not the same thing as having the ability to effectively teach it. Lee Shulman defined this distinction as pedagogical content knowledge, or PCK. It is the specialized cognitive translation of a discipline into teachable subject matter. Deep PCK allows a teacher to instantly recognize the specific cognitive hurdles, historical contexts, and representational models unique to their subject. Generic best practices fail because they lack the specific domain logic required for this critical translation step. Without deep domain PCK, a teacher defaults to reciting facts rather than guiding students through the process of disciplinary discovery. A subject culture does not blindly script classroom action. It must be actively and expertly translated by a specialized practitioner. Finally, we must account for the teacher's internal, personal mediation of the subject culture. Institutional directives and academic cultures are always filtered through the teacher's own unique worldview. This mediating filter is known as a teacher's aesthetic understanding. It is comprised of a teacher's passion for the topic, the coherence of their mental models, and their resulting professional identity. This framework explains the current crisis of out-of-field teaching in secondary education. An out-of-field teacher lacks this aesthetic coherence. They do not possess the internalized narratives needed to seamlessly link the curriculum to their students' lives. The friction of out-of-field teaching is not a failure of general instructional skill, but an alienation from the target discipline's underlying cultural epistemology. Today, many educational administrations rely on standardized instructional checklists to evaluate and guide STEM classrooms, but generic descriptors of effective teaching break down when applied to specific disciplinary epistemologies. Treating mathematical sequence and scientific phenomena as an interchangeable administrative block is a structural error. Ignoring these deep structural differences places an unsustainable cognitive and cultural load on teachers who are forced out of their specialty. Schools must stop treating pedagogy as a blunt, universal tool. Success in the classroom requires the right instrument for the subject. True improvement requires inducting teachers into the specific traditions, language, and aesthetics of their distinct discipline. To effectively teach a subject, one must do more than deliver its facts. One must actively inhabit its culture.